Okay, so then we'll start the lecture for today. Thank you all for coming. We're going to today discuss some aspects of the Hilbert space in AdS. In some sense, this is a very simple discussion, but nevertheless, we're going to try and say some things which, are not usually emphasized. This is in build up for what we will do tomorrow and perhaps also the next week. This principle that we were just discussing right now, which is the fact that in gravity, there's a reduction in the number of degrees of freedom. And there's a sense in which gravity stores information very differently from ordinary quantum field theories, in that if you give me data outside a ball, you've also told me what's happening inside a ball. But that's something that we'll come to tomorrow. Today, we are just discussing some very simple things about field theories and gravity in AdS. So the discussion that we're having today is applicable. I want to emphasize both for quantum field theories in AdS and also for theories of gravity in AdS. Let me just remind you of what the metric of AdS is. Just to be completely concrete, we are going to discuss not Poincare AdS, but global AdS. The reason for this is just, that it gives us, if you're in global AdS, you have a calculator. In fact, we will discuss in some detail also the similar story in flat space, where we will have to deal with IR issues. So global AdS you can think of as a warm-up, and it allows us to focus on things without worrying about the metric of global AdS. When I write this metric, I've set the AdS scale to be 1. Let me remind you that, as usual, we are considering AdS d plus 1. This is, in fact, the convention that we have adopted in other lectures as well. The dimension of spacetime is always d plus 1. So the way you should think about this geometry is roughly as a solid cylinder. I mean, where time goes upwards. So one way to think about this geometry is to think about something like this. This is the sphere direction is the one that goes around. This is the radial direction, and this is the time direction. Okay, so this is a good way to picturize the geometry, and the geometry you should think of as being a box. Okay. Now, as I said, we will also discuss theories of gravity in AdS. When we discuss quantum field theory in AdS, we can just take this metric that I've written right now on the board to be a fixed metric, and then we don't have to worry about the metric itself fluctuating. But in general, if you want to deal with theories of gravity, then it's important that this is not an equality, but what we are specifying is only the asymptotic behavior of the metric as r goes to infinity. So we are saying that as r goes to infinity, the metric tends to this metric that we have written. It may be the case that there are other subleading terms, which we will discuss a little bit later, but the leading term in the metric is what we have on the board. And also, when we discuss a theory of gravity, it's important that we'll never be in the regime where gravity is strongly coupled. And one measure of that, which we'll use in this lecture and also as we go forward, in fact, perhaps for the rest of the course, is that there's a natural scale, which is just given by this AdS scale divided by the Planck scale. Okay? So one way to think about this physically is that we are talking about the ratio of the cosmological scale. So you have some universe, there's a cosmological constant, there's a length scale set by the cosmological constant. And we have, that scale set by the cosmological constant is much, much, much longer than the scale set by the Planck length. So there's a big gap between these two, and we are going to take the regime where n is much greater than 1. Okay? So this is the sense in which gravity is weakly coupled. In fact, not only are we going to say that n is much greater than 1, whenever we talk about this, we will also take n to be larger than other order 1 numbers in the game. So n is larger than all other numbers. Okay. I mean, unless those numbers involve n itself. What that means is that, we might at other points talk about other things. We might talk about high energy states where high energy is high energy with respect to the AdS scale, but even that will be low energy with respect to n unless we explicitly put in a factor of n. So this is just notation as we go forward, which is useful to keep in mind. Okay. This is also the standard convention that's used in AdS CFT, but in any case, this is the convention that we are going to use. Okay, great. So this is just some simple stuff about the geometry of AdS, which I hope many of you are already familiar with. First, let me just start by reminding you of the Hilbert space of a simple scalar field in AdS, and then we will discuss how this generalizes when you allow the scalar field to interact with gravity and with other things. But to start with, let's just consider a single minimally coupled scalar field sitting inside AdS. So a minimally coupled scalar field is just one that obeys some simple equation. It obeys an equation which depending is so we just have some what convention did I choose for the metric? Probably I should have a plus. Okay. So it just obeys some simple equation, which is the Klein-Gordon equation for the field. Before we look for solutions to this equation, it's important, in fact, as we were just discussing, to say something about the boundary conditions with which we look for solutions. So we are interested in this minimally coupled scalar field, and we are going to impose the boundary condition that phi tends to 0 as r tends to infinity. Let me just explain what this boundary condition means, especially for those of you who are familiar with Euclidean AdS-CFT. When we do Euclidean AdS-CFT, you often look for solutions to the equations where, in the case where m is 0, phi doesn't tend to 0 as r tends to infinity, but phi tends to some constant, or you specify some data on the boundary of AdS for phi as r tends to infinity. However, it's important that physically, as you know, corresponds to taking the theory as it stands and deforming it with a source. So the boundary condition that we have imposed here is the boundary condition that involves the autonomous evolution of phi. So these boundary conditions are also called normalizable boundary conditions. So phi vanishes near the boundary. And indeed, it is the case that, if you were to start with some nice finite energy initial data and you were not to turn on some sources, you don't try and, deform the theory in some way, deform the Hamiltonian of the theory, then these are indeed the natural kinds of boundary conditions to impose. It might be of interest to impose other kinds of boundary conditions where, you deform the theory or you allow the field to leak out, and we'll discuss maybe in a few lectures from now this notion of transparent boundary conditions. But for now, the simplest setup is where you just allow the theory to evolve autonomously, and this corresponds to these normalizable boundary conditions as r tends to infinity. Okay? In fact, every question that we want to ask about the theory, you can ask by imposing these boundary conditions. So, when for those of you who've studied AdS-CFT and how to compute correlation functions, it's often, people often talk about formulating AdS-CFT by turning on sources. But in fact, every question you want to ask about either the bulk theory or the boundary theory, you can also study by just allowing the theory to evolve autonomously without ever talking about sources. I mean, that's always true of quantum field theories. It might sometimes be convenient to talk about sources, but every correlation function and everything else you want to talk about can also be framed without talking about sources. In fact, that's kind of a nicer way in some ways to think about the theory, because you're not disturbing it and you don't have to worry about what the disturbance causes. So in any case, we are going to consider these normalizable boundary conditions. With these boundary conditions, you can solve this equation that I have written down. Let me not go through the details of how you solve it. It's a pretty simple exercise in separating variables. And I'll just write down for you the solution to this equation with these boundary conditions. So the solution to this equation turns out. So it's a linear equation, and therefore arbitrary solutions are sums of these equations. I'll explain what these constants are in a minute. Okay. Okay. We might just as well, since we are solving the equation, solve it for a quantum field operator rather than just looking at classical solutions. It's the same thing in this linear setup. So these ANLs are going to be annihilation operators, these CNLs, and the other notation I'm explaining in a minute. This chi NL R is the following function. And then there's some hypergeometric function which is not of so much interest, but it's good to write it down just once, just to make sure we know what we are talking about. Okay. Okay, and the CNL, this term that we have here, okay, this is a normalization factor that you can find in the published review. It's some horrible normalization factor involving ratios of gamma functions, which is not going to be of interest to us, but it's a normalization factor, and you can find the explicit expression in the review. Okay. Okay. So what is what are the features of? Sorry, Chandramouli, is there some issue with the host is changing?
Yeah, actually lost connection from a laptop.
Oh, I see. Fine. Okay. Now it's okay, right?
Yeah.
Okay, great. Fine. Okay. Fine. So CNL is some normalization factor, and let me just point out some salient features of this solution. One of the features of this solution is that this solution, even though we actually impose this boundary condition, which you see here, which is that phi goes to 0 as r tends to infinity, the solutions that we find actually have the property that phi dies off with a particular power of r, which is 1 over r to the power delta, okay? Where delta is some characteristic coefficient that depends on the mass, okay, and happens to be this. Okay. So in fact, even though we just look for solutions which die off at large R, we find that they actually die off in a particular way at large R, and they die off as 1 over R to the delta. But there's a second interesting aspect of these solutions. Let me just copy the solution and let me point out what these, let me explain this in a little more detail. So these solutions actually have various features. Okay, one of them is that apart from the fact that they die off as r to the delta, they oscillate in some way, and it turns out that these solutions are quantized solutions. Okay, so you don't have a continuum of solutions; you have a quantized set of solutions, and the reason you have this quantized set of solutions is because if you think of the picture that we drew in the beginning, you will see that this AdS is like a box. And we demanded that this field die off near r tends to infinity. And whenever you do that in a box, you find that you end up with solutions that oscillate some number of times in the box. But they have to oscillate, they can't oscillate with arbitrary frequencies. They have to oscillate in some specific way. And that is what tells you that these frequencies that you see here are quantized in a very specific way as 2n plus L plus delta. And this n controls this radial part of the wave function, which, as I explained in the previous slide, was some kind of hypergeometric function. Apart from this, there is also some quantized sphere on the d-1 sphere, which I have written here in terms of this spherical harmonic, which is labeled by a single, I've just written down L. In fact, as you know, spherical harmonics are labeled by more quantum numbers. But none of those quantum numbers are ever going to be of any interest to us. So, I've just used this L to stand for all the quantum numbers of the harmonic. And apart from that L, the other quantum number which is of interest is this number n. And this number n appears and is a quantum number because of the boundary conditions that we have put, these normalizable boundary conditions that we have put. And that forces the field to oscillate in a certain way, and it quantizes the frequencies that we have. Okay? And if you normalize these solutions correctly with this CNL, with this normalization factor, then indeed you will find that these ANLs obey canonical commutation relations, as I will explain in a minute. Okay. Are there any questions about this issue of classical solutions? If there are people who are not familiar with it, if there are any, I'm assuming that this is just a recap, but if there are, if there are questions about these classical solutions, I can answer them and then we can go forward. Okay. So I guess people are familiar with these classical solutions in AdS. As I said, the field dies off as r to the power delta, and it's convenient often to talk about the asymptotic value of the field, which is limit as r tends to infinity r to the delta into phi of r t omega. Okay? So the field is a function of r, t, and omega. But you can ask what happens to the field as you go asymptotically far away. And there's some boundary value of the field, which is, I said the field lies off as 1 over r to the delta, but you can pick up the boundary value. And that, in fact, defines an operator in the quantum theory, which you call OT omega. In AdS CFT, even though we will not in this lecture necessarily make reference to AdS CFT, but in AdS CFT, this operator O is the operator that is dual to this bulk field phi. So this O and this phi are related in this way. And the way you find the dual operator is by taking the bulk field, taking it to infinity, and by stripping off the leading fall off. And when you do that, you end up with this bulk operator. There's some interesting relation between the modes of this operator and the modes of this bulk field. You can write down, I wrote down this operator in space-time, but you might also want to write down the modes of this operator. And of course, the way you would write down the modes of the operator is just by doing a Fourier transform. Okay. And if you did this Fourier transform, you would then pick up the modes of the operator. And these modes of the operator are related to these modes that we have, that we wrote down previously, as ONL is square root of GNL into ANL. Right now is for us just a definition. It's just, whatever appears. It's because I said every solution dies off as 1 over r to the delta. And therefore, there's a coefficient that appears. And the coefficient that appears is, I'm just calling GNL. But in fact, this coefficient is an interesting coefficient, although we won't explore it more. That is because I said that these ANLs were normalized canonically so that they satisfy some relation of this kind. Okay? And you see that in this situation, these ONLs commute with a factor of GNL. So in fact, this GNL is like the Green's function, or is like the commutator of these generalized free fields. So you can also get it by computing the commutator, or by computing the 2-point function of these fields in the boundary, and by taking the Fourier transform. But if you wanted to do a bulk computation, this is what you would do. Okay? There's a question which asks about in what sense are O and phi dual to each other. Here I was just making reference to the fact that in AdS CFT, when you have a bulk field, there is an operator which is dual to that operator, and I was using the sense dual in the sense of that, in the sense of this AdS CFT duality. But if you're not familiar with AdS CFT, then you can just take O right now to be the boundary value of phi as r tends to infinity. But it's also true that there's a sense in which fields in the bulk are dual to operators on the boundary, and that's the sense in which I was using the word duality. Okay, great. So now let me just say, so far so good. This has all been just elementary quantum field theory in AdS. Let me now just say, yeah.
Can you repeat what is GNL here?
Okay, let me write down the expression. So GNL is just some factor. In fact, square root GNL happens to be gamma of L plus N plus delta. Okay. You see, this factor is of interest because this factor is telling you, it's kind of telling you what ONL dagger is. Remember, ANL dagger is just 1, right? ANL into ANL dagger is 1. But ONL times ONL dagger is not 1. It's this factor. And this factor arises because, when you look at the 2-point function of this field in AdS CFT would be dual to some generalized free field. It would be a primary operator of dimension delta. It would have a 2-point function on the boundary. And this 2-point function on the boundary would have some Fourier transform. You could take this 2-point function on the boundary and Fourier transform it. And this would be the Fourier transform, because the Fourier transform of ONL dagger will give you, ONL dagger gives you GNL. And this GNL, as you can see, is indeed the Fourier transform of the 2-point function of O. And that's why this GNL is related to something. It's the 2-point function in Fourier space. But for us, it's simply the fact that when you take the field phi and you take it to infinity, there's some fall off, which is r to the delta. You pick up the coefficient of that fall off, that gives you square root of GNL, and that's this expression. But it's if you could get it in a totally different way, by computing the 2-point function in the boundary, and that would have to match with what you have here. Does that answer the question?
Yes, thank you.
Okay, thank you. Great. So we have these modes, these creation and annihilation operators, and now let's just proceed to construct the Hilbert space first within perturbation theory. Okay. So within perturbation theory, the construction of the Hilbert space is very simple, right? We start with a vacuum 0, and what do we demand? We 0 for all NL. Okay. Remember, just so you don't get confused with the notation has an AN and it has an L, and this L is a collective quantum number for all these harmonic, for all these spherical harmonics, and this N is like the radial quantum number. Okay. So we see that AN, this is how you would usually define the perturbative vacuum. This is what we are taught in QFT 101. And once you've defined this perturbative vacuum, we just have a free field, and therefore you could define excitations on top of this vacuum just by creating excitations. Right? So you create a Fock space. It's a very simple kind of Fock space, right? Because you have these discrete modes, and you would create excitations of this kind, and you could keep going. Each of these excitations has some energy. We discussed, as you could see from the frequency dependence, these A and L excitations had some energy, which was 2n plus L plus delta. All of these excitations that we have here have some energy. And therefore, if you schematically look at how the Hilbert space looks like, you have a vacuum here. And then apart from the vacuum, you have some other states. Oops. And you have some states at some energy levels. Okay? If there were different kinds of fields of different masses, you would have different kinds of energy levels. Some of these energy levels in the free field approximation are degenerate. They have to be degenerate because, you could have different values. You could have different, even for a given value of L, you could have different angular, you could have different spherical harmonics with different angular quantum numbers. And therefore, these E's are not, when I plot them this way, I don't mean that they're non-degenerate. They could be degenerate, but I'm just pointing out that there are these gaps in the spectrum. And this is how the simple low energy spectrum looks like, which you get just by quantizing free fields about AdS. Okay. Now, of course, if you were to turn on interactions, then you would have to break some of these degeneracies. Some of the degeneracies might persist if there are conserved charges that commute with the Hamiltonian. Others might be broken. And of course, these energy gaps would shift. In fact, these energy gaps in AdS CFT are dual to the spectrum of operator dimensions. So these energies that we see in AdS are dual to the operator spectrum of operator dimensions in the dual CFT. And the fact that they shift when you turn on interactions corresponds to the fact that these operator dimensions pick up anomalous dimensions when you turn on interactions. Okay, but in any case, the qualitative picture we still expect to persist. We don't expect that the interactions, because we're in this weak coupling limit, will pull this energy level down to 0, or will cause degeneracies at 0. We still expect that these things will get shifted, but there'll still be some spectrum of discrete energy eigenstates, and the details of that spectrum will not be important for anything that we say. Okay, good. So far what we've said has been very simple and has just been within a perturbative free field theory. Now I want to say the first thing, which might be somewhat, I want to now generalize and explain how you can think of this Hilbert space in a very general sense, and even in the presence of gravity, when you might worry that, in the presence of gravity, you don't know the Hilbert space. But I want to show you how, just starting with this very simple perturbative picture, you can generalize and obtain a simple description of the Hilbert space, or at least it's an overcomplete description, but you can at least obtain a simple overcomplete description of the Hilbert space. So let me just motivate that starting with this picture. So, I generated these modes right now by saying that, you took these A and L daggers, these creation operators, and you acted in the vacuum with them. But of course, I could have done something else. And the other thing I could have done is, rather than taking these creation operators of the field, I could have taken this boundary field that I had. Okay? I could have taken this boundary field and I could have pulled out the boundary operator that created this mode. Right? So I could have, done this kind of an integral. and I could have acted with this operator on 0. Okay, so I've written down a complicated kind of expression, but in fact, this whole thing is actually something pretty simple. Okay, I'm just trying to extract O and L dagger. And to extract O and L dagger, I'm just doing a Fourier transform, and I'm pulling out some mode that pulls out, the term which varies with like e to the I 2n plus L plus delta, and then something which varies with YL. Okay, so I'm just pulling out O and L dagger. And you see, I've done this by taking this boundary operator OT omega and integrating it with some space-time function. Okay, good. Now you see that by what we just said, this generates in free field theory. This generates a state which is parallel. It's not normalized correctly, but generates a state parallel to ANL dagger on 0. Okay, great. So now I could also generate the other states in the Fock space in the same way, right? I could take one of these operators. Let me just take this guy and let me just copy it twice. Right? So let's paste it once, and then let's paste it again. Okay. So now I need to add some symbols. So let me add 1, 1, 1. This is dd minus 1 omega 1, 1, 2, 2, 2, 2, dt1, dt2. And I can add also twice n1, L1, and twice n2, L2. Okay. So I haven't done anything deep. I just took 2 of these operators, and then instead of acting on the vacuum with like one of them, I acted on the vacuum with the product of 2 of them. Okay. And this, of course, will generate for you some state which is parallel to AN1 L1 dagger and AN2 L2 acting on the vacuum. Right? So this is just a simple, it's the fact that instead of acting with these creation and annihilation modes, I can take these operators or these asymptotic operators, and I can act. Okay, so in general, this Hilbert space that I have described, I can also describe in a slightly different way. And the different way to describe the Hilbert space is that I can also take these asymptotic operators, I can smear them with some space-time functions, and then I can act on the vacuum, and I can think of the span of all such states. Okay. Whereby O of f, I mean integral O of t omega into f of t omega, okay, dt and dd minus 1 omega. Okay. Here we've been discussing states where the f's have been integrated only from 0 to pi, and that's because that's the AdS like crossing time in some in free field theory. But in general, if I take this f to be of compact support, I could do an integral for a larger range. Okay? And it's clear that these kinds of operators where you take O, you smear it with some space-time function, and you act in the vacuum, will generate for you the same kind of Hilbert space that we had previously, where you took the vacuum and you tried to generate a Fock space by acting on it with creation and annihilation operators. Okay? So far, I think this is just a different description, which is a pretty simple description of the same Hilbert space. Okay, now why am I making such a big deal about this description, right? It almost seems like I'm doing some trivialities. I had some Fock space. I had some, in the Fock space, I had some way of exciting the Fock space with creation operators. And then I said, oh, by the way, we can also take the creation operators. We can write them in terms of some operators in the boundary. Okay? So this operator OF is some operator that lives, it's some operator which is near the boundary.
So,
yeah, just give me 1 second, please. Okay. So can you give me 1 second, please? I'll come to this. Yeah. So you take some operator O of f, you smear it on the boundary, you act in the vacuum, and that gives you the same Hilbert space. And so far, so it sounds like it's just a triviality, but in fact, this is going to be something pretty interesting, which I'll describe. Okay, but let me take the question before I describe that. Yeah, go ahead, Shreyans.
So I couldn't understand. So can you please move to the previous page.
Yeah.
So how are we defining A dagger NL?
Remember, I said that the limit of phi t omega, right? So we had ONL, which was square root of GNL times ANL. Okay. And that was, if you just take phi and you integrate it with time, you will pull out ONL. I mean, so this is the definition of ONL dagger, which is square root of GNL times ANL dagger.
It's the Fourier transform of O T omega. Okay.
Correct, with a particular frequency and a particular spherical harmonic. Correct. Right. As I described before, these modes of O are parallel to these A's. I mean, there's some normalization. So, the state is not exactly ANL dagger, and that's why I wrote the state is parallel to ANL dagger on 0. You could normalize it correctly, but that's not important for us. So these states that we have here are not normalized, but they generate the same Hilbert space once you take the span.
So shouldn't A dagger be O dagger, the Hermitian conjugate of the O field?
There is a Hermitian. I mean, I don't know. The field O is Hermitian.
Okay. So no, I didn't got that. A and A dagger in that case would be similar.
Okay.
So O, shouldn't it be O dagger T of omega is equal to A dagger NL?
No, I think this is correct. Maybe we can discuss this offline. The field O is Hermitian. So the field O has both O's and O daggers inside it. I integrated with e to the minus I to n plus L plus delta. Previously, to extract ON, I had integrated with e to the I to n. So you can extract either the positive or the negative frequency components. You just by convention call one of them ONL and the other ONL dagger. I mean, it's not convention. It's the fact that one of them has positive energy, the other has negative energy. And so this integral will extract, the function I'm smearing it with is not a real function. It's some complex function. That's why it extracts ONL dagger. Okay. Thank you.
Suvrat, I have, yeah. So about this geometry, the diagram that you have drawn, why is it a cylinder? I mean, R seems to go till infinity.
Okay. So you have to compactify R. You have to go to coordinates. You can go to coordinates where R is compact and varies between 0 to pi by 2. I mean, the reason I draw it is this way is that if you draw light rays here will go on 45 degrees. So this is not quite a Penrose diagram, because to draw a Penrose diagram, you should compactify time as well. But this is the diagram in which light rays travel at 45 degrees.
Right. Okay. Got
That's
it.
right. Okay. And that's a good question. The reason AdS, yeah, you're right. So, it might seem that the coordinate length of AdS is infinity, right? R is going off to infinity. But the point is that light can cross from one side of AdS to the other side of AdS in a finite time. And that's why, we say it looks like a box. Okay, thank you. Okay, now very good. So now, why was I making a big deal out of this description? So the reason is the following. This description that I have actually permits a very nice generalization, both to the interacting theory and to gravity. Okay? So this is very useful both in the interacting theory and in gravity. Okay? And let me explain why it's so useful. Okay? It's also useful in gravity. Okay, let me first explain why this description of the Hilbert space is very useful in the interacting theory. Okay, so you see, in the interacting theory, it's important that the interacting theory also has some Hamiltonian. And when we talk about the vacuum, we'll talk about we're not talking about the Fock vacuum. In the interacting theory, we should define the vacuum as the operator that's annihilated by the Hamiltonian. Now, just to say here, the Hamiltonian might have some 0-point energy. So you might want to talk about the lowest eigenstate of the Hamiltonian, but it's going to be convenient for us always to shift the 0-point energy so the lowest eigenvalue is 0. This is just a matter of convenience for what we're doing. You're free to work with some other 0-point energy if you like, and sometimes it is convenient to think of a 0-point energy. But for everything we're doing, we can always just shift away that 0-point energy. Okay. So now this Hamiltonian is this vacuum is defined as a state which is annihilated by the Hamiltonian. Now consider the set of operators which are OT1 to OTN on 0. Okay. I want to point out here that I have dropped the omegas. I'm going to drop the omegas. I was keeping them so far, but I'm going to drop them now because they're not going to be important and I don't want to keep writing omega every time. So I'm just going to write OT1. Whenever you see OT1, you should actually think of OT1 with an omega. So, the boundary is not just time. The boundary is time across the cylinder, across the sphere. But, the sphere coordinate, as I said, is a sideshow for us. So we can always think of these operators, which are OT1 into OTN times omega. If you like, you can think of this being smeared with some spherical harmonic on the sphere. But the important part for us is the time coordinate. And think of an operator of this kind. Okay? Now, what happens, and you take an operator of this kind, which is a product of O's at different times, and you act on it with the vacuum. Okay? Act on the vacuum with it. If you wanted to get a state which was normalizable, you would probably need to smear this a little bit in time as well, with some functions in time. But for now, let's just forget about that, because what I want to show you is the question you could ask is, what happens to this state if you evolve it in time? Okay? So let's say you start with this state at some point, and then you evolve the state a little bit in time. Okay? And then you could ask, what does this state go to if you evolve the state in time? If you evolve the state in time, you will find the following remarkable fact. Okay? So let's say you try to evolve it in time. Evolution is just given by this operator e to the minus IH tau. Okay. If you evolve the state in time, then of course you multiply it with e to the minus IH tau, but then you could insert ones in all of these places. And you could keep inserting ones, and then in the end you would have once again something which looked like e to the minus IH tau, e to the IH tau on 0. Okay, is it clear? I had an e to the minus IH tau, and then I didn't do anything. I just inserted ones. Okay? So I've inserted ones between all of these operators. Okay? But now, oh, I inserted ones the wrong way. I should have inserted it this way. But now, if you stare at this operator, notice this is sandwiched between an e to the minus IH tau and an e to the plus IH tau. Right? But this is just the time evolution of the operator O of t by the time tau, actually by the time minus tau. Okay? So all of these operators that you have, okay, are just being shifted by t goes to t minus tau. What about this last expression that we have here? This last expression, actually, this last factor of e to the minus IH tau, when it acts on the vacuum, doesn't do anything because of this condition that you had here. If you had a 0-point energy, it would give you an overall phase. But either way, it gives you something trivial. And for us, even that phase is just 1. Therefore, this whole expression, you can simplify and you can write in the following way. Maybe. So you can simplify this whole expression and you can write it just as O of t1 minus tau, O of t2 minus tau, and O of tn minus tau acting on 0. Okay. But this, I could just redefine my times and call them t1 prime, t2 prime, t3 prime. So I could just call this O of t1 prime, O of t2 prime, okay, and O of tn prime acting on 0. Okay. So the interesting thing is that a state of this form, evolves under time evolution to another state of the same form. So if you start with a state where you take these T1s to be arbitrary, so you don't restrict the T1s in some way, and you do time evolution, then you end up with yet another state of the same form. Okay? And this is true in the interacting theory as well. In fact, this is also true in a theory of gravity. The reason this is true in a theory of gravity is that in a theory of gravity, although what we do in the bulk doesn't, the bulk might be fluctuating, whenever you define a theory of quantum gravity, you always keep the asymptotic boundary fixed. And on the asymptotic boundary, you still have a notion of time translations, and those time translations will do exactly what we are seeing here. Okay? So this statement, because it's a statement about asymptotic operators and not some operators in the bulk, is true not only in an interacting quantum field theory, but it's also true in a theory of gravity. Okay? So the interesting fact we have here is that if you look at the span of these states, if you look at the span of some O's smeared with some functions on the boundary, if you look at the span of these states, this set of states forms a superselection sector. It forms a superselection sector in that under time evolution, it evolves to itself. So you might have other states in the theory. You might decide to say, well, I want to include some other states in the theory, but you can never start with a state of this kind and evolve into one of those other states. Okay. So this description of the Hilbert space, even though we started by saying something very simple, by talking about, perturbative theory and saying, I could generate all the states by taking these O's and smearing them on the boundary and acting in the vacuum, in fact, is a very good description of the Hilbert space. And it's such a good description that it's a good description even in a theory of gravity, where you can still define these asymptotic operators, you can still smear them. And even in a theory of gravity, this forms a superselection sector in the sense that it's closed under time evolution.
I have a question.
Yeah.
Sorry, I still didn't get the point behind smearing.
Sorry, Akhil, could you please speak up?
Yeah, so I still didn't understand the point behind why smearing was important.
Oh, the smearing was just important just to ensure that the states have finite norm. If you take these operators all operators, local operators in quantum field theory are, they have, you should think of them. You always need to smear them so as to get like smooth 2-point functions. You don't want to worry about what happens if the operators come to close and some norms diverge and so on. So if you just take O of T1 acting on the vacuum and you try and look at the norm of that state, that norm is actually divergent because you'll get O of T1, if you compute the norm of just O of T at a single point, the norm of this state is infinity because, the norm of this state is, which doesn't make any sense, right?
Okay.
That's just the product of two operators at the same point.
Okay.
So if you smear it, then you get a state of finite norm.
Which is like the usual reason why we smear all fields.
Yeah. It's the usual reason why you smear.
So, and secondly, what do you mean by states of this type?
States of this type, I mean that, I haven't written it very formally, but I mean that you should smear O, you could vary N, for instance. So when I'm saying states of this type, N here, and I'm allowed to vary these smearing functions. So you could try, basically what I mean to say, you look at, states of this type in that you're allowed to consider states of this kind, you're allowed to consider states of this kind, okay, with arbitrary F1 and F2, arbitrary F1, F2, F3, and so on. That's what I mean by states of this type.
So you mean the number of traces in the boundary traces?
The number of entries can change, and the smearing functions can also change. So the smearing functions can change over some smooth functions which have compact support.
Okay, thank you.
Okay, is that good? Okay.
Suvrat, I think, Rifat, please go on. Yeah.
If you take bulk operators and smear them and then take and compose them in the same fashion as you did for the boundary operators and take the span, is it like equal to the span that you have on the board, or is it something larger than that?
This is actually, so this Hilbert space is a closed space, right? So it won't, in a general quantum field theory also, it would not give you anything that was larger. This would give you the full Hilbert space because you don't have interesting closed sectors in a general interacting theory. But let me just say, this is also not very different from, you are taking a particular limit of bulk operators. So let me remind you that this O of T was always like limit as R tends to infinity of R to the delta into 5TR. Now your question is, if I did this, if I also allowed to vary over all R, would I get a larger span? In general, in a general interacting theory, you would not, because you would not have interesting closed, super selection sectors. So it would not be that, there's some set of states which you get, which just don't evolve to these other states. Maybe in some cases you might, but the point for us is that, considerations of unitarity cannot force us to enlarge this space. So even if there is some sense in which there are larger states that exist only in the bulk and that never come out to the boundary, we don't have to care about them because, we can just start with the set of states and be in the set of states forever.
Okay.
I can't give you a proof that bulk operators would not give you a larger span, but there's an expectation that they would not because, generally things evolve to everything else. So, you don't have a closed dynamical sector. But the formal statement is that the sector on top is a super selection sector.
Or maybe you mean like the span that you have on the board is something like a dense subset of the span of the bulk operator smeared out.
Well, actually, so far I haven't said anything about a dense subset. I just meant that this is a super selection sector. But yeah, you could talk about how this fits within the larger set and if it densely fits within that. Okay, that's a very subtle question. I don't know how. I'm not sure how to answer. Whether there are some. But it's clear. It could be. Let me just say. It could be that there are some states which you get in the bulk. So maybe in some theory of, for instance, it could be. Let me give you an example. Sometimes people talk about theories of gravity and they talk about these so-called bags of gold states. Okay? So it could be that there are some states like these bags of gold states which are not of this form. Okay? So physically, the way you should think of these states is they're states which you're producing by starting with the vacuum on the boundary and by throwing in stuff. It could be that there are some states which are not of this form. In that case, you would just, we would just say we would not care about them. Let me also say something else. In AdS CFT, it's clear that this is the entire Hilbert space. So in AdS CFT, this is the set of states you get by acting with all asymptotic boundary operators, and it's clear it's the entire Hilbert space. But in general, can you have some other theory of gravity where you have some other bulk states? You probably could, but it's important that this is a super selection sector. So even if there are such bags of gold states, you don't have to worry about them.
Okay, thank you.
Okay. So now let me say the following thing. Okay, there's some point where maybe some of you were worried about this. You could have asked me. I said at some point that this is also valid in a theory of gravity. This is a good description of the Hilbert space in gravity. And the reason it's a good description is because asymptotic operators make sense. And this Hilbert space was defined by looking at these asymptotic operators. Okay? Now you could have said, wait, there's something kind of funny about this. Okay? The asymptotic operators I was talking about were asymptotic operators which were obtained by taking some field phi and by taking its limit as r goes to infinity. Okay? Now, if you take a limit, and also the other thing was asymptotic time translations make sense. But you could have said, you took some field phi, and that was some light field phi, right? And you define some asymptotic operator based on that. But we know that in a theory of gravity, if you're talking about quantum gravity, the Hilbert space should be much larger. Right? It should be much larger. It should have black holes. It should have strings. It should have d-branes. We know you shouldn't be able to formulate a theory of gravity without all of this stuff. So where did all of this stuff go? If some of you didn't have this question, you should have had this question. You should have said, this doesn't make any sense. You're talking about operators, which are some asymptotic quantum field operators. You take them to infinity, fine, okay, they make sense in gravity. But we know that there are other stuff in gravity, and where did all of that go? Okay. So, and I also said that, this looks like a dynamically closed sector, and so, you shouldn't have to worry about this other stuff. But you should have said, but you should have had to worry about branes. You would not be able to formulate gravity just by looking at these excitations. Okay, so the point is that this is actually something which is very nice, and the point is that even though in the theory of gravity you would have all of these non-perturbative states, you would have branes and you would have black holes and all this stuff. All those states you would still be able to produce by looking at this very simple set of states. Okay. What is the physical reason? First of all, we just have a proof, right? We have a proof which is that this is a super selection sector, and that proof doesn't depend on anything. And so, if in a theory of gravity, we have both of these things being true, that asymptotic operators make sense, which we expect because you hold asymptotic boundary conditions fixed in gravity. And if it's true that, the Hamiltonian leads to asymptotic time translations, then, it would be the case that this set of states that we have is closed under time evolution, and therefore it's dynamically closed. So we have a proof. And the reason the proof makes physical sense is because you should think of what we are doing here. So what we are doing here is that we are taking the vacuum and we are throwing in some stuff from the boundary. Okay? So we are throwing in stuff from the boundary. So this is what these O of Fs are doing. Okay, so these O of Fs are like, the physical way to think about them is you start with the vacuum and you throw in stuff from the boundary. When you do that, you do in fact end up evolving to all of these interesting states that we know about. Okay? So you do some time evolution with this. Let me extend my cylinder a little bit. Okay? You throw in all of this stuff, you have an interacting theory, and when you do that, you will end up evolving to black holes and brains and everything else. Okay? So this is the horizon, a black hole has formed. And the reason was, I just threw in some bunch of gravitons and I waited for a long enough time. And in the end, I will get a horizon. It's important that to get black holes and all of these states, you'll have to throw in a lot of energy. Okay. So to get all of these states, you might have to act with like O of F1, O of Fn. You might need to act with them a lot of times. You might need to act with them n times. But the point is, when you do that, all of these other states will emerge from dynamical evolution. So there is one description of these states in terms of black holes, but you can also think of them by just starting with the vacuum and by acting on it with these asymptotic operators and smearing them with arbitrary space-time descriptions. Okay? So this is kind of a, so that, this is the magic of time evolution, okay? Is that you don't actually need a description where you start with, where you don't explicitly need some description in terms of brains and black holes and so on. If you just want a complete basis for the Hilbert space, this gives you a complete basis for the Hilbert space. Okay. Now I've said something about magic, so there's always a little bit of illusion involved in magic. Magic always involves illusion. And so there is something else which I should immediately say. And that is that this Hilbert space that I have written down, okay, this Hilbert space is actually an overcomplete Hilbert space. It's overcomplete because, you can see even here, even in perturbation theory, that if I were to take F1 to be e to the I into 2n plus L plus delta for t in 0 to pi, okay, or if I was to take it to be e to the, or if I was to take it to be, if I take F2 being the same thing, but in the interval pi to 2 pi, you see you'll get the same state. So this is a trivial example where even in free field theory, you can see that two different functions have, these are different functions. One function has support in 0 to pi, the other function has support in pi to 2 pi. Two different functions will give you the same state. In fact, in the interacting theory and in a theory of gravity, you will have a lot of such relations, and the relations will be much more complicated than the trivial relation you see in front, where sometimes you might have two states like OF1 and OF2, which both generate the same state. So OF1 on 0 is equal to OF2 on 0 in the free field limit. In general, in gravity, you might have many, many more relations. And we know you have such relations because this description that I've written down is not so useful for counting the entropy. You could ask very meaningful questions about the Hilbert space. These are the kinds of questions that have been asked and answered successfully in string theory, which is, you could say, let me look at the set of states at some energy, which is of order n, and let me count how many states there are at that energy. And that's a well-defined question. And this description of the Hilbert space that I have given you does not help in answering that question. Okay, so this basis that we have is an overcomplete basis, and it's it is a super selection sector, so it is complete. It spans all states, but for some kinds of questions, it's not very useful. So even though there is a sense in which it includes black holes and brains and everything else, and that happens because of the magic of time evolution, there's another sense in which this may not be a very useful description of the Hilbert space. But for our purposes and what we want to do, this is a useful description. For some other purposes, it may not be a useful description because of what I just said. Okay, I hope this is clear. Are there any questions about this? Because now I'm going to say something that might be even more confusing.
Can you hear me?
Yeah, I can hear.
So what do you mean when you say that you throw in some gravitons and then let it evolve with time?
Yeah. If you think of the state, thank you. So let's say you think of the state which is like O of F1, O of F2, 1, 0. Okay. Let's say you thought of this state in the weak field limit. So I didn't actually, I was not talking about gravitons here. These were some fields, but this is just a 2-particle excitation. Now, if I could create like a very high particle excitation as well by acting with like O of F3, O of F4. I mean, I could act with like many operators, and I could create a very high particle excitation. And that in the weak field limit is just some gas of gravitons, or it's some gas of these massive particles that I was throwing in. If this O was the graviton field, then this would be a gas of gravitons. Then I can allow it to evolve with time. You see, I'm allowed to then do time evolution with this. And time evolution might cause this gas to collapse into a black hole. Right? In the end, how did we discover black holes? We discovered black holes by saying, you have a gas of matter, like ordinary matter, you excite that, you wait for some time, and then it evolves into a black hole. And so, what I was trying to answer was that you could have had the following question. You could have said, all the particles all the states you're writing down here look just like multi-particle gas of graviton states. But I'm pointing out that, in fact, these states do include also other states which you might have called non-perturbative, such as black holes and brains. And that's because you can start with some excitation, which is a very general excitation of gravitons and other kinds of particles, just quantum field particles. You can excite them from asymptotic infinity. And time evolution will then take you to all of these interesting states that we usually think. It was only to prove this statement, which is that this span, where these are asymptotic operators, gives you, does indeed form a superselection sector. It forms a superselection sector even in gravity, even though you might have thought that there are operators, states like black holes, which are not described here, right? Because there's no such thing as a black hole quantum field. There's no such thing as a brain quantum field. So you could have said, where are the black hole states here? The point is they are living here, and they're just living here in some hidden form. Does that answer the question?
Yes.
Okay, thank you. Are there any other questions about this? If this is confusing.
Sorry, I have a naive question. So when you have dynamical gravity, that means you have these asymptotic operators corresponding to these excitations of gravitons as well, right? Not just the scalar.
Yes.
Oh, okay. Yeah.
Yes, indeed. I was just kind of assuming that. I started off by talking about a massive field, but this was just for illustration. Okay, so indeed, I started off by this. This was for illustration. Indeed, when you have dynamical gravity, you will have other quantum fields as well. One of those fields will be the graviton itself. You might have gauge fields. You might have fields of different masses and so on. I started off with a field phi just to illustrate this O, but in general, this O doesn't have to be like a scalar operator. It might be an operator which has indices. So it might be like the stress tensor operator in the dual CFT. It might be the operator that's dual to the graviton.
Yeah, and when you have, global AdS, what you have shown is that the Fock space, you have discrete energy spectrums, right?
Yes.
But that's not true, for instance, when you have a black hole in the AdS. So
it is not, gone,
So, doesn't the structure of the Hilbert space fundamentally change once you have black hole?
Yeah, so what happens is actually this is the low energy structure. If you keep going to high energies, in the end, what happens is that at very, very high energies, the energy gaps become very small. In fact, these gaps become of order e to the minus n in what we have defined things. So there is indeed, there are gaps in the energy levels. The Hilbert space is always discrete because in the end, you expect that you have some well-defined boundary theory that lives in compact volume. So the Hilbert space is discrete, but you're right that it's very hard to see the gaps in energy levels because of this e to the minus n. And that's why it was important that, we had this result which said that, exactly. So you could have asked this question. You could have said, here I am defining like these states. These states are just defined by taking O, smearing it with some operators F and acting on 0. And you could have said, where are all these states which are very tightly, which have these small gaps and so on. The point is they are living there. So if you take the Hamiltonian, you try and diagonalize it in this, you should get this spectrum of energy eigenstates. That's a hopelessly complicated exercise, but the proof that this is a superselection sector is just a very simple proof. That's the proof that we did here. Okay, so it's just obviously true that if you take this set of states, it doesn't evolve to anything else except for itself. And because we know that the interactions of gravity do produce black holes and so on, this means that, this is the only set of states that we need to look at. Okay? So you're right, you could have asked, how do you see these small energy gaps? How do you see the entropy, which is related to a question I asked earlier about, how do you see the entropy? And it's very hard to see from this description the precise value of these energy gaps. But the fact that, this set of states forms a superselection sector or gives you a basis, that's clear.
Thank you.
That's all we're going to need. Okay, let me say one last thing let me say the last important point I wanted to make today. So now I want to do something which might be a little confusing. I want to describe how you can squeeze this Hilbert space. Okay. So far I said that, you describe the Hilbert space by taking the span of these asymptotic operators, smearing them, acting on the vacuum. Now I'm going to say something which is, and already, it's a surprising statement, how could this work? I'm going to say something that might be even more surprising. So I'm going to say that we can produce the same space by acting. So when I say same space, I'll have to be a little careful, but let's think of the space where you act with, where these f tildes are now functions have support only in a small time band of size 0 to epsilon. Okay? So I claim that this space, okay, is dense in the original Hilbert space. Okay. So notice what I'm saying. Earlier, I said that there was a physical interpretation of the Hilbert space that we were looking at. And the physical interpretation was that we had global AdS, and then we started throwing in some stuff at all possible times. Okay. And we got some set of states by doing that. Now I'm saying you can get the same set of states by throwing in stuff in a small interval of size 0 to epsilon. Okay, so I hope the sense of the statement is clear. We will now prove it. But it's a first I was saying, and at least it was plausible in some sense that there are these gravitons. You throw the gravitons, you throw them at all times. You can throw lots of them. Therefore, you generate all states. But now I'm telling you that in fact you could choose to just throw in particles or excite these asymptotic operators in a very small time band where this epsilon can be any finite number, and that would give you a state which is basically the same Hilbert space. Okay? So I'm now going to prove this result. But let me first emphasize before we go forward. I cannot emphasize this enough actually. Let me emphasize here. Okay. So let me. Okay. This result is true in QFT and in gravity. Okay. So this is not what we are calling the principle of holography of information. Okay. So this result is not, it doesn't have anything to do with holography of information or the information paradox or anything. It's just some simple result that's true in QFT and in gravity, but this is not the principle of holography of information. Okay. And the reason it is not is that, this result I want to emphasize holds also in QFT and in gravity. And QFT doesn't have any special way of storing information. QFTs store information the same way as classical as our intuition suggests. And in fact, to prove this result, you could have just started with this massive scalar field, made it interacting, and this result that I'm going to prove would still be true. It's also true in a theory of gravity, but this doesn't have anything to do with how information is stored near the boundary. I mean, it'll be an input later into that, but by itself, it doesn't tell us that information is all available near the boundary. I'll emphasize this again in different ways, but I want to emphasize even before we start that this result is true in quantum field theory and also in gravity. Okay, so let me prove this result. How do you prove this result? Okay, let's start first by looking at single particle states. Okay, so let's consider states of the kind O into F on 0. Okay, The notation I'm going to adopt is that when I have f, this function f can have arbitrary support, and I will distinguish this from the functions f tilde, which are functions which have support only in 0 to epsilon. Okay? So let's say you had a state psi. You looked at the set of states which were obtained by taking one copy of this asymptotic operator, smearing it with some function in space-time, and acting on the vacuum with it. Okay? Now, say it was the case. Okay, say this was orthogonal, okay, to all states O of f tilde on 0, okay, where f tilde has support in 0 to epsilon. So I hope the structure of the argument is clear. I'm going to argue by contradiction. So let us say the statement I made previously was not true. Say there was a state that I could take by smearing O with a function be orthogonal to the functions, to the set of all states I could obtain by smearing this O with functions with support only in 0 to epsilon. Okay? So I'm going to prove that if that was the case, it would lead to a contradiction. Okay? So if this was the case, then it would be the case that this state psi has the property for all tau in 0 to epsilon. Another notation I'll try and stick to is that this tau will be in 0 to epsilon. Okay. So as opposed to t, which can be arbitrary, I'll try and stick to this tau just for this lecture being in 0 to epsilon. Okay. Is it clear that, you know, if psi is orthogonal to all states you can produce by by smearing O with this function f tilde, then it must be the case that, you know, psi, the matrix element of O of tau between psi and the vacuum is 0. Right? Because if the matrix element was not 0 for some tau, then it's clear that this state psi is not orthogonal to O of tau acting on 0 for whatever value of tau the matrix element is not 0 for. Okay? Is this statement clear? Okay, I'll assume it's clear. If it's not clear, please ask a question.
Yeah, could you repeat the reasoning once again? Yeah,
you see, let us say this was, you see, psi is orthogonal to all states of the form O of f tilde 0, right? This is the state of the form O of f tilde 0, because it's like, I mean, it's when you take f tilde to be a delta function, right? When you take it to be a delta function around tau, this is a state which you get by acting with O of tilde on 0. If psi is orthogonal to all such states, then it must be orthogonal to this kind of a state. This is a state, right? So it must be the case that the matrix element of psi, you know, or the matrix of O between psi and the vacuum is 0.
Right. Thanks.
Okay, great. Excellent. So now this is the case, but now, you know, even in the theory of gravity, we expect that there is some Hamiltonian and some spectrum of energy eigenstates, and we can still do quantum mechanics the way we do usually. So this matrix element, I can insert a complete set of energy eigenstates, and I can write it as psi of E into E of tau on 0. Okay. But this E of tau on 0 is something very simple, because this is just psi of E into E O on at time 0 on 0 into a factor of E to the IE tau. That's because this is the sum over energy eigenstates. I inserted a complete basis of energy eigenstates here. That's what you see here. And then in this energy eigenstate, I know what O of tau is, right? Because this O of tau is just e to the minus e to the IH tau, O of 0 e to the minus IH tau. And then I can just act with this e to the IH tau on this E, and that gives me this factor of e to the IE tau. Okay? So it's clear that the psi O of tau on 0 is an expression of this kind. But notice that this expression has a nice property. It has the property that this is analytic when tau is extended in the upper half plane. In the upper half plane, okay, not in the lower half plane. Right? It's analytic when tau is extended in the upper half plane, and that's because whenever you extend tau in the upper half plane, you get a factor of e to the minus IE tau from here. So I'm using here the positivity of energy. And it's the fact that whenever you extend tau in the upper half plane, you just take the same correlator and you get e to the minus IE tau. Okay? So the same correlator, if it's defined for this real tau, will only be better defined as you extend tau in the upper half plane. And therefore, you see it doesn't have any singularities because it has these factors of e to the IE tau for positive e. It doesn't have any singularities whenever tau has a positive imaginary part. So this correlator doesn't have any singularities when tau has a positive imaginary part, and it's analytic when tau is extended in the upper half plane. But now we have an interesting situation of a function which is 0 in 0 to epsilon. Okay? So it's 0 here, and it's analytic in the upper half plane. Okay? When this is the case, I mean, there are standard theorems in complex analysis that tell you if you have a function which is 0, which vanishes here, and it is analytic in the upper half plane, this function must vanish everywhere on the real line. And the reason is pretty simple. Because this function is analytic on the upper half plane, because it vanishes in the 0 to epsilon, you can analytically continue it from here and get some value here. In fact, because it vanishes in the 0 to epsilon, you can also write down an analytic continuation on the lower half plane, which is just 0, and that also gives you 0. Okay? So you have a function which vanishes. I drew too many arrows, but what I was saying was actually pretty simple. You have a function which vanishes on 0 to epsilon, which is analytic in the upper half plane. So you can analytically continue this function to the upper half plane and reach some other value, maybe -1 or 1. Okay, but because this function vanishes in 0 to epsilon, you can also analytically continue to the lower half plane, and you can reach the same value from the lower half plane. Both ways, you just reach 0. Okay, so if this function vanishes between 0 to epsilon, this function must be 0 everywhere on the real line. So the argument we had previously, this tells us that psi O of tau 0 vanishes for all real tau. But now we are in trouble. We are in trouble because we said psi was of the form O of f on 0. So it cannot be the case that psi, actually I should use t as I promised, because now I'm allowing t to vary over the entire real axis. It cannot be the case that psi and O of t0 is 0 for all t, because psi itself was produced by taking O and smearing it with some function f. And therefore, it must be the case that psi O of t 0 into f of t, like this is actually the norm of psi, and this cannot be 0. So we've reached a contradiction. We've reached a contradiction with the fact that if we said that psi was O of f on 0, then we would have found that psi O of t, so let me just recap what the argument was. We started with this state of this form O of f on 0. We said, let us assume that it was orthogonal to all states which were produced by acting with 0 to epsilon. We found that if it was orthogonal to all states which were acting on 0 to epsilon, it would in fact have to be the case. There was an intermediate argument, but the final result was, if it was orthogonal to all states in 0 to epsilon, it would actually have to be orthogonal to all states produced by the action of O of t on 0 for all real t. But that would be in contradiction with the assumption that psi itself was of this form. Okay. Therefore, psi cannot be orthogonal to all states that are formed by the action of O of f tilde. It cannot even have any orthogonal, like it cannot have an orthogonal component to all states that are produced by the action of O of f tilde on the vacuum. Okay. Okay, so this tells us that all states you can produce by smearing O on a larger time band, you can also produce by smearing O on a smaller time band. Okay. Now, let me make the same argument. Let me just tell you how the same argument works for multi-particle states. Are there any questions at this point?
Yeah, I have a question.
Yeah.
So the fact that it does have non-zero overlap doesn't mean I can create that state purely in a small window.
Yeah. Thank you for the question. You see, let's say there was some state which yeah, good. You see, let's say there was some state which was of the form O of f psi. Right? Let's say there was some state of this kind, which you couldn't create from O of f tilde psi, right? Say there was an element which could not be created, right? Or which always had some finite overlap, which could not be approximated arbitrarily well. So let's say there was always like a finite residual. Okay. Then you see, you could just take a linear combination of these states O of f tilde, and you would find some O. So we could find then some G, so that O of G on 0 is orthogonal. Do you see the logic? Let's say it was the case that you always found, that there was some residue that you could never approximate, right? Let's say there was some orthogonal direction in the action of O of f on 0. If that's the case, then you could take a linear combination of these states and you would end up with some state that was orthogonal to the original space. Right? So it's not just that you have to have, so, if you have, the point is there is no state in the larger space that's orthogonal to the action of O of f tilde on 0. And that tells you that O of f tilde on 0 is actually dense in the big Hilbert space. If it's not dense, there would be some state in the bigger space which would be orthogonal to the action of O of f tilde on 0. Is the logic clear?
Okay, and could you also say when you say approximated arbitrarily, what are we approximating with?
Yeah, the approximated arbitrarily was the statement that what we really proved is that the state, the set of states O of f tilde is dense. You can't have a finite residual, but it might be that so this is the mathematical difference.
I'm slightly confused about are we approximating in epsilon and also are these statements true in all orders in n or 1 by n and so on?
So at this indeed, so this statement, this is just an exact statement. It's the fact that this is not a perturbative statement. This is some exact statement which is true. And I was just saying that, what this tells you is that you can't have a finite remainder. There's no finite vector which lives in the bigger space, which is not, but it could be that you can only ever get arbitrarily close. You can only approximate it better and better from the smaller Hilbert space. You need to take an infinite sequence to actually get arbitrarily close. It's only in the limit that you actually get the state in the bigger Hilbert space. Okay. Actually, this is not something that is ever going to be important for us. But what we actually proved is you can't have a finite remainder. You can't have a remainder of finite norm. Does that answer the question?
Yeah, I'm slightly confused. What do you mean by remainder of finite norm? As in,
there can't be a state of this kind which has finite norm, which is orthogonal to all states f of f tilde. If you're confused about, we can just, you can't have there's no state of finite norm in the bigger Hilbert space, which is orthogonal to all states that you can get by acting in the smaller time band.
Mm-hmm.
Okay, so you don't have to worry about like the subtleties of, further subtleties of that. This is, it's a question of whether you can approximate, for instance, can you approximate real numbers arbitrarily well by rational numbers? So there's no real number which is finitely separated from a rational number. That's what we really prove. Okay. Beyond that, there's nothing of physical significance in what we are saying. Does this answer the question? I hope.
Yeah, I'm worried about things like whether the overlap could be like epsilon power n or whatever, and then are we? Because okay. Epsilon is a small parameter, and I could have things which go like epsilon power n, which I might think is 0 because epsilon is 0. But once you continue away from the
epsilon is not 0, and there's nothing perturbative here, so you could make the overlap as small as you like. You could try and ask. Maybe you could say that how many, if you had some basis of functions from 0 to epsilon, how many elements of that basis would you need to include in order to be able to approximate this function well? And maybe in an interacting theory, you would need to include very high elements of the basis to approximate it arbitrarily well. But so far, this is just a statement which, when I'm saying dense, it's dense in some mathematical sense.
Okay.
Maybe we can talk more offline.
Okay, thanks.
Okay, thanks. Okay.
Suvrat, I have a question.
Yeah.
So you showed that the state psi, which is O of f acting on ket0, is not orthogonal to some O of x acting on ket0 when x belongs to from that time interval 0 to epsilon.
Correct.
What tells me that I can't smear O with some smearing function which has support only in that time interval, and for some special smearing function, even that cannot be orthogonal to psi.
Sorry, I didn't understand. What was?
So we have psi, which is O of f acting on ket0, and let's take psi tilde, which is O of f tilde acting on ket0, f tilde with support from 0 to epsilon.
Yes.
Yes, you proved that the overlap is 0 if the smearing function instead of smearing function f tilde, I just inserted that operator at one particular point.
Yeah, just to say, it's not the case that the overlap can never be 0 if I take arbitrary f and arbitrary f tilde. It's the fact that the span of all states you get with O of f on 0 is the same as the span of all states you get with O of f tilde on 0, where you allow f to vary over all functions in the larger interval and f tilde to vary over all functions in the smaller interval. It's not the statement that you can't select a specific f tilde so that psi on f tilde 0 is 0. That, of course, you can do. You can always select some particular f tilde so that you can always find some, let's call it g tilde to avoid. You can always find some g tilde so that this is 0, right? If I say find me a g tilde so that this is 0, sure, you can find a g tilde. The point is that it can't be 0 for all tau. If it was 0 for all tau and it was 0 for all g tilde, then you would be in trouble. So it's not that it's not 0 for any g tilde. It's the fact that it can't be 0 for all g tilde.
So you mean like if I change g tilde by a very small amount, like I'm changing the function by a small amount, then this thing might be 0. But if I fine tune g tilde to a specific function, then it is exactly 0. In that sense, you're saying this is dense in that, is it?
No. So just the point is that what we proved is that we cannot have. So the statement was we cannot have psi O of tau 0 equal to 0 for tau in 0 epsilon without having, if this is the case, then it implies that psi O of tau 0 is 0 for all real tau. This was the statement we proved. So if psi itself, psi O of tau 0 can't be 0 for all tau in 0 to epsilon. That was all we said. So this was the precise statement we proved. And therefore, if psi itself was of the form O of f acting on 0, it could not be that psi O of tau on 0 was 0 for all tau in 0 to epsilon. Okay, maybe you can come back to questions. Since you have only 5 minutes left, let me just try and prove the multi-particle version of this. So, in general, we said that we have this Hilbert space. This Hilbert space was produced by O of f1 on O of fn on 0. The claim is we can get the same space. When I say same, it's in the sense we were just discussing, in that you can approximate any vector arbitrarily well. We can get the same space through O of f tilde, O of fn tilde on 0, where fi tilde have support in 0 to epsilon. Okay, so now how do you prove this statement? It's the same way. Okay, imagine that we had a state psi of this kind, which was orthogonal. So let's say we had a state psi. Let me just erase this. Which was orthogonal. Okay, so let's say psi was orthogonal to all such states. Then it would be the case that psi on O of tau 1, O of tau n on 0 is equal to 0 for all tau 1, tau 2, tau n in 0 to epsilon. Okay. This is the only way psi can be orthogonal to O of tau smeared with arbitrary functions in 0 to epsilon if these matrix elements are just 0 for all tau 1 to tau n being in 0 to epsilon. Okay, but now let's just start inserting complete sets of energy eigenstates between all of these guys. Okay, so if we insert, sorry, I should put first an energy eigenstate. So let me just insert energy eigenstates between all of these guys. And here I get the end. E2. Okay, so this I've just inserted between all of these operators O tau 1 to tau n, I have inserted these energy eigenstates. Okay. Okay. But now you can do the same trick that we did previously, right? In fact, if you do this trick, you will find that this is just psi E1, E1, O of 0, E2, En, O of 0, into 0, and times some number of phases. Okay. The phases you get look like e to the I into E1. Okay. But now look at how E1 multiplies tau 1. Okay. But look at what E2 multiplies. Okay. E to the I E2 into tau 2 minus tau 1. That's because E2 also picks up a phase from this other operator here, which I have not displayed. So E2 multiplies tau 2 minus tau 1. E1 just multiplies tau 1 because E1 just picks up a coefficient from here. But E2 picks up something from here. And I can keep going in this way till I get e to the I En into tau n minus tau n minus 1. Okay. But now I can change variables in the following way. I can write Z1 is equal to tau 1, Z2 is equal to tau 2 minus tau 1, and so on. Zn is equal to tau n minus 1. And then this correlator that I have is analytic when Zi are extended in the upper half plane. Okay. And then you need to invoke a more fancy theorem from complex analysis. It's called the edge of the wedge theorem. Which you can look up. The edge of the wedge theorem is proved, for example, in this book, PCT spin statistics and all that by Whiteman and Streeter. There's also this description by Witten in these notes on algebraic quantum field theory, which will prove a simpler version of this same statement. But there's a similar result that tells you that if this correlator vanishes, so the result is again the same using this analyticity property. If this correlator vanishes for all tau in 0 to epsilon, then it vanishes for all real tau. And now we are in trouble because we assumed that psi was a state of the kind O of f1 up to O of fn acting on 0, okay, which is in contradiction with our initial assumption that psi was of this form. Okay. Okay. So this is the statement that even states of this kind, where you take O of f1 to O of fn, you act in a larger time band, you can get just by acting in a smaller time band. Okay. Okay. This is actually all I wanted to say. Let me just conclude with a few very small comments. This is a trivial example of the so-called Reeh-Schlieder theorem. So sometimes you will see similar theorems proved under the name of the Reeh-Schlieder theorem. The reason I say it's a trivial example, the reason I say it's trivial is because we consider the entire boundary. The entire boundary between time 0 to epsilon. In general, the Reeh-Schlieder theorem is often in quantum field theory used to prove a stronger statement about any open set. But we didn't do that. We considered the entire boundary between time 0 to epsilon. And we said acting with, we consider the whole sphere between 0 to epsilon. And we said the space of states obtained by taking O, smearing it with some function in the time band 0 to epsilon, acting on the vacuum gives you something that is dense in the big Hilbert space. And we didn't try and restrict also where you on the sphere. On the other hand, what we have proved is valid also for gravity. In general, the Reeh-Schlieder theorem does not hold for theories of gravity in its strongest form. It certainly has not been proved, and for theories of gravity, it's even hard to make sense of the Reeh-Schlieder theorem in general. But what we proved, because we were just talking about asymptotic operators, is valid also for gravity. And the only assumption we made, and that's the reason why it was a trivial example, the only assumption we made, we only used the positivity of energy. In general, the Reeh-Schlieder theorem uses something stronger. It uses something called the spectrum condition. We didn't need that because we are considering this very special case. And because we are considering this very special case, we only needed the positivity of energy, and that we expect to hold even in the theory of gravity. Okay, so today has been a detour in discussing some aspects of the AdS Hilbert space which are not emphasized. It might not be entirely clear what the object of the detour is, although these issues I think are interesting in their own right. These issues of what the structure of the Hilbert space in AdS are interesting, I think, anyway. But tomorrow we'll come back and say something that has more relevance for questions of quantum information, where we'll discuss something special, how this results in more special dynamical properties of gravity. Tell us something nice about how quantum information is stored in gravity. But this is all I wanted to say for today. So I'll stop here and we can take more questions.
Hi, I have a question. So
yeah.
did we not assume that the operators are time ordered in this case?
No, we did not assume the operators are time ordered.
The fact that Z1, we assumed specific signs for Z1, Z2, etc.
No, the operators were not time ordered. They were just ordered. It just was O of tau 1 came first and O of tau n came later. So that's what allowed me to have O of, you see, if I had time ordering, it would have been different. Notice that what was happening here was I got O of tau into tau 2 minus tau 1. And the reason I got this was because tau 1 came first. And then here there was a tau 2, which I didn't write, but there would have been a tau 2 here.
But don't we assume that Z2 is positive?
No, we don't assume Z2 is positive, but this correlator is analytic when Zi are extended in the upper half plane. Z2 may or may not be positive. The real part of Z2 may or may not be positive, but the imaginary part of Zi has to be positive. So the real part of Z2 has undefined sign. We don't care about it. All we said is that this is analytic when the imaginary part is taken to be positive. Okay, so this is not a time ordered.
So these statements are true for like any ordered correlators.
This is I picked a specific ordering. If I picked a different ordering, notice that when I picked an ordering, I got Z2 being tau 2 minus tau 1, and it was this which had to be. So if you think in the original coordinates, it is the fact that tau 2 has to have a larger imaginary part than tau 1. So tau n has to have a larger imaginary part than tau.
Yeah. So that I understood. But
yeah, so that's what's happening.
I'm asking about the real part of tau 2.
Yeah, for the real part is true for arbitrary real part. Yeah. So when you continue from the Euclidean theory to the Lorentzian theory, as you know, this is how you get a particular ordering in the Lorentzian theory. You take the imaginary parts to 0 in a particular way, where you take this one to be the largest and then this one to be the smallest. And if you do that, then you will get an ordering which is of this kind, where the one with the smallest imaginary part comes on the left and this one comes on the right.
Yeah, but usually when you talk about out of time ordered correlators in holography and so on, you have to wait order of log n time to really see their effect, right? They are really suppressed initially, but you
wait order of log n times before you see.
As in the OTOs are the growing exponent part of the OTOs are suppressed by a factor of 1 by n or 1 by n square.
Sorry, but there's nothing we said about any growing exponent or any chaos or anything here. This is just a 2-point function. It's not. I mean, it's not like the 2-point. Yeah.
I'm just confused that I could really create an out of time ordered state within a epsilon time window. Is that?
Sorry, there's no notion of an out of time ordered state. What you're talking about is something from chaos, which is not relevant here. This is just the fact that you start with O of t and you act with O of t1 and O of t2. You act on the vacuum with it. That creates a state. the state I was labeling with T1 and T2, which just told me the ordering of the operators, that state is not a zero norm or anything, or for small norm. So, you could take O of t, smear it with some f, take O of t, smear it with some other f, act on 0. You would get some state. In the free field example that I gave you, for instance, this would just be some nice norm state of some finite norm. So there's, the fact that some correlator, I mean, what you're talking about is not, I don't see the direct relevance to what we're discussing here.
Okay, I was under the impression that like if certain states where the string of O's we act with to create the state, if the string is out of time ordered, it's probably not you cannot probably make the state with the time ordered string of operators. I was just kind of assuming that.
I'm not sure why I'm not sure that if you're confused about this, just think of the free field example. In the free field example, you could take these states star O of t, smear it with some f's, take O of t2, smear it with some f, act on 0. In fact, that would be the natural way to do it. So you would get creation and annihilation operators for both. You could then consider some other set of states where you took some time. When you're trying to create states, it's not so natural to consider some time ordered action of operators, but you could consider some time ordered action of operators and try and get the same set of states. But if you're just trying to create states, it's very natural to take O of t, smear it with some f independently, take O of t2, smear it with some f independently, and then act on the vacuum. And that's why you have to pick the ordering, because the smearing is just you're smearing the first variable in some way and the second one in some way. And this is like acting with O of n1 dagger with O of nn dagger. Right? So there's in the free. So the thing you're thinking about quantum chaos and so on is not relevant here. There's no direct relevance to what we're discussing here.
Okay, thanks.
As far as I can see.
I have a question. So your OF tildes, which we're using to create all these states, were defined, had support on some particular time band, right?
Yes.
But that is a co-dimension one sort of a space inside your space-time. And Reeh-Schlieder talks about open support on open sets. So I don't know. Yeah.
It's not co-dimension anything actually. It has the same dimension. So if this was t equal to if this is the boundary of AdS, I'm saying that you can create states by just acting with something here. So it's not co-dimension anything. So this is what we proved. That you have some time band here. And we proved you could create everything by acting with operators in this region. Now, in general, there's some more general statement which is true in Minkowski space, which is the simplest case, which is if you just take Minkowski space and you just take any open set anywhere, then it's true that you can generate the entire Hilbert space by acting with operators from this open set. This would you might want to try and prove something by just taking some open set somewhere in the bulk, but whatever statement you prove there, you'd be very hard pressed to make it work for gravity, because if you try and talk about bulk open sets in the bulk, that's not something that's easy to define or make sense in a theory of gravity. You could prove an analogous statement on the boundary, which we won't need. If you could try and prove that let's say you take some open set on the boundary, then can you generate all states? And you could prove such a statement under slightly stronger assumptions than we used. You'd need a little bit more than the positivity of energy. You would need some notion of the spectrum condition on the boundary, which you could take because we do have some symmetry on the boundary, and we have a notion of angular momentum and of energy on the boundary. And so you could try and prove a stronger statement on the boundary. You could try and say, instead of taking the whole time band, I could just take like some diamond on the boundary, and you could prove a stronger version of the theorem there, but we will not need that, and that's why I didn't prove it.
But the support of F tildes exists on just this time band, right? So
Yes.
How is that an open set? Because it's just at some radial slice. We've taken R to infinity over here, but it doesn't extend over the R.
Sorry, I didn't understand. What is the
support of F tilde that you?
Yes.
That you...
So this F. I mean, so I'm not. So I was saying there's some other version of Reeh-Schlieder which you usually use. This is a particularly simple version where you've taken the entire time band and you've gone all around the boundary. So what is the? I'm not sure what the confusion is.
So I'm saying the support of F tilde still does not seem to be an open set. It's at some particular radius. It's a very large radius. It's a very large R, but it is. Still...
Oh, you're worried about why you're not going a little bit into the bulk.
Right.
That's what you're saying. Oh, I see. Good. So this going up in time a little bit avoids your having to go up in the bulk. So you could have asked intuitively, you could have said, how is it that you're doing everything at r tends to infinity? So roughly, going up in time a little bit helps you. If you draw, let me just draw the diagram again. This thing that we were drawing, which was, that's a good question. This is 0 to epsilon. So I'm just drawing a cross section. In a quantum field theory, you can think of this as describing this causal wedge in the bulk. So you can think of operators in this time band as describing some causal wedge in the bulk. So in fact, you could think that, by going in this time band 0 to epsilon, you could alternately think of it by going a little bit into the bulk as well.
Oh, okay, got it.
That's a physical way to think of it. What we proved is just an independent and true statement. And that's because we proved that you could first generate the Hilbert space by going at r tends to infinity, acting with asymptotic operators. But you could have had this question of why you didn't have to go into the bulk a little bit. In some sense, we did, but these are all just words. What we proved was a precise statement.
Right. Okay. Thanks.
Okay, thank you. Yeah. Are there any other questions?
Hi, sorry, I got confused with the last thing that you said. So for O tilde, we are also going into the bulk, right, for a small region? No,
we are not going into the bulk. I said it's equivalent. We are always on the boundary. These O's are asymptotic operators, right? So these are asymptotic operators.
I was thinking of them as like you take a small width even in R, and then from R1 to R2, and you send both R1 and R2 to infinity with keeping the width size constant.
You might need to do that in some way to take the limit, but that all I said was if you take O of t omega from with t in 0 to epsilon, then this is actually the same as phi on r t equal to 0 omega, with r being I forget exactly, but probably cot between infinity to cot epsilon. Yeah, I think that I maybe cot epsilon by 2. I forget exactly, but if this taking O of t omega is like in the free field approximation is approximately like taking phi, but at t equal to 0 between the range infinity to some cot epsilon. So you could physically think of going in this time band as going into the bulk. But what we proved is you just take the asymptotic operator and move a little bit in the time band. We actually didn't say you will go into the bulk. I'm just trying to give some physically equivalent statement, but that's actually imprecise. The precise statement is you just act with O of t omega for t equal to 0 to epsilon.
Okay. And can I expect Reeh-Schlieder theorem to hold in semi-classical gravity when gravity is kept classical but still dynamical?
Yeah, I think so. I mean, the theorem we proved is very general. It would hold even in the presence when gravity was entirely dynamical, because it would hold under the assumption that the original Hilbert space you started with is this Hilbert space, which is O of t acting, take O of t, O of t1, O of t2, O of tn, smear it with functions, act in the vacuum with it. And provided that was the case, you would be able to generate the same space by acting with, O of t smeared in a smaller band from 0 to epsilon. You could talk about other situations. You could try and do, maybe what you're asking is, can you do this if you have if you try and do quantum field theory in a black hole background or something like that, and you keep the black hole fixed. So there you would have to be careful about the fact that you don't have a well-defined notion of a vacuum. So in whatever we are using here, we had a notion of a Hamiltonian, and there was a vacuum, and we are generating things on top of that vacuum. So you would need to be careful that you do have such a notion of a vacuum if you try and do QFT about a fixed background.
My understanding was Reeh-Schlieder theorem was proved for in any arbitrary fixed background.
So the Reeh-Schlieder theorem, you can't prove an arbitrary fixed background in curve space. You have to make some assumptions about what the spectrum of excitations is. But, so there's some general version of the Reeh-Schlieder theorem you could try and prove, which is you take some curve space, and in a quantum field theory, you just take some open set somewhere in the curve space, and then you try and ask, can you generate the Hilbert space from there? In general, that would be hard to prove. You'd need to make some assumptions about the spectrum of excitations. But I want to emphasize that what we did, we just proved in some ab initio way. We have a particularly simple and useful version, which is going to be useful for us, which didn't involve any assumptions. The only assumption we needed was the positivity of energy. So now there are many other theorems you might try and prove, and you could prove them with assumptions about the spectrum of energies and so on. But first of all, many of those theorems would not work the moment you included dynamical gravity, and some of those theorems would require further assumptions. We have a simple version which works in the presence of dynamical gravity under a particularly simple assumption, which is just the positivity of energy.
Okay. And I have one last question.
Yeah.
I'm confused about something in the beginning of the lecture.
Yeah.
So can you go to that page where you drew those spectrum?
Here. Yeah.
Yeah. So here what you're doing is you're just taking free field theory and putting it on and fixed AdS background, and you're quantized free field theory. And the spectrum for that theory is this.
Exactly.
Okay. For that theory, you have Hilbert space, and then you said that that Hilbert space is also equal to the span of O1, O2 acting on Ket0.
Exactly.
Okay.
And as I said, that description also works in the interacting theory.
Okay, that description also works in interacting theory. So still, I'm in the regime of quantum field theory in Gauss space-time, and over here in this Hilbert space, I would not expect some state to describe a black hole state because I'm keeping the background fixed.
In this Hilbert space, you would not. In this quantum field theory, you would not. Yes.
Yes, and then later you said that this space that you get by the span of O1, O2 acting on K0, in that space, I can think of a state in that space to also describe some black hole in the bulk.
Exactly. So you turn on, yeah, that's exactly. So, we said that was somewhere here. I said, so we'll turn on interacting theory. So you could turn on interactions. So we started with this description, which just looked like O of F1 to O of Fn acting on 0. Then we said, well, now let's turn on interactions and let's also turn on gravity in principle. And then the thing we proved was that if you took this set of states is actually closed under time evolution. Okay. So the important result is that this is a super selection sector. And this is just a result we proved, right? This is a result which is true even if you have gravity in the bulk. And so the statement is that this kind of set of states doesn't evolve to anything else. Therefore, in gravity, you expect that, in some cases that whenever you have a black hole formed from collapse, it does form from this set of states.
Yes.
It's telling you that this set of states does include black holes and does include a whole set of interesting things. And you might have wondered where they came from, and they came from the fact that time evolution and interactions generated them. But the fact that this selection sector is just exactly true. So the fact that it's a super selection sector is just true even in the presence of interactions. So that was the interesting thing. And then we said, well, this is an interesting Hilbert space in that it does include black holes and so on because interactions generate them. And for that, it was important that this description was not a free field description anymore. It was a description which was true in general.
So my confusion is exactly at this point. I agree that yes, if I turn on interactions and eventually since this is a super selection sector, if I evolve in time, I'll be in this sector, and I know that from physics, in a physical argument, the state will form black hole.
Yes.
So, but how do I know that the formalism that we have written down that describes things like the black hole forming or something like that? I know in the real world black hole will form, but it's not necessary that the formalism that I've written down will will agree with what I expect physically, right? Because this looks like a QFT curve spacetime formalism alone.
So the point is, let's say, good. So maybe one way to think about this is the following. Let's say you have some theory of gravity or you have string theory. Okay. Even if you have string theory, there is some sense in which there is a notion of asymptotic operators. I mean, in any theory of quantum gravity, you still do have a notion of asymptotic operators. So even in some, the description of the full theory might be very complicated, might involve like all sorts of other complicated things. But as long as there is a good notion of asymptotic operators, as long as, when you go to asymptotic infinity, there's some sense in which you can talk about these quantum field operators. There is a good sense in which you can define this Hilbert space, and this Hilbert space is still, forms a super selection sector, which probably means it's, it captures everything that's dynamically interesting. So the point, you're right that maybe to have a leg to stand on, you should say, let's say we do have some complete theory of quantum gravity. In that theory of quantum gravity, provided asymptotic operators make sense, this Hilbert space forms a super selection sector.
Okay, so so in the theory of quantum gravity, we expect this to happen.
Yes.
We are not logically concluding this from semi-classical gravity or anything.
No, we are not logically showing that. So we are not logically showing that yeah, it could be that, maybe that this theory we started with is in the swampland. You need to include like all sorts of other things. So it's not like we have any deep consistency conditions on this Hilbert space. All we are saying is that if you do have a well-defined theory of quantum gravity, in that theory of quantum gravity, we expect asymptotic operators to make sense. And then this Hilbert space forms a superselection sector.
Okay. And last question is, if I just restrict myself to QFT spacetime, I cannot conclude this. But if I restrict to the region in which I'm talking about semi-classical gravity, can I conclude this thing?
This is actually, there's no question of semi-classical here. This statement was now true under arbitrary interactions, including cases, not just in the low energy theory, but including in the case where you had gravity and allowed arbitrary states in the bulk. So this is a stronger statement than just saying we have semi-classical gravity, right? It's a statement that even when you have full quantum gravity, you keep the asymptotic region fixed. And there's a sense of talking about asymptotic operators, which are local operators. Even in flat space, you talk about an S matrix. The S matrix still makes sense even in string theory. In AdS as well, there's a sense in which you can take the asymptotic limits of operators, and that still makes sense. So these OFs are those operators, and even if your bulk is fluctuating and doing all sorts of crazy things, this Hilbert space is still, forms a good superselection sector, provided these asymptotic operators make sense, which we usually expect they do.
Okay.
Because asymptotically things still make things behave the way you don't expect gravitational effects to be strong if you go off to infinity.
Okay. Thank you.
Okay, thank you. Okay, I guess we've depleted most people. So
is there still time for one more question?
Yeah, sure. Yeah, go on. Yeah.
Okay, great.
Yeah.
Because I was trying to make sense of what this means physically.
Yeah.
Should I interpret this result as the fact that in a deterministic theory, if you have the information on a small time band, well, then basically you have the information for all times, because if you know the state at a particular time.
No, you should not interpret today's result as being that result at all. So today's result is that's what I was trying to emphasize here. So we will try and prove such a result tomorrow, but that's only true in gravity. Today's result was true in QFT and in gravity, and it is not true in QFT that if you have information for 0 to epsilon, that you know everything that's happening in the bulk. In particular, you could have unitary operators in the bulk which commute with all operators that are there in the boundary. So I'll try and emphasize this in the beginning of tomorrow's lecture.
Okay, so I don't mean necessarily the bulk, but you have the information for all possible times, right? I mean,
no. If in a QFT where this result would still be true, it's not true that from today's result that if you have information from 0 to epsilon, you have information about what's happening later, because you could have stuff that's coming from the bulk and hitting you later in a QFT. So from what we have proved, the fact that you can generate all states, that's not enough to actually give you all information about what's happening in the bulk. And that's why I wanted to emphasize this fact that, it's not true. This result that we proved today is a result also in a QFT. There is a result we will prove tomorrow that if you have information in the small time band, you have information for all times. But that result will require us to invoke a property of gravity, which we'll discuss tomorrow. So, tomorrow there'll be a divergence between how QFT behaves and how gravity behaves. So it will be true in gravity, but it will not be true in QFT that if you have information for small time band, you have information for all times.
okay, then I think I'm a bit confused what it means that you can construct the state, because whatever the state is in the future, you're able to construct it.
Yeah. So I was thinking of doing tomorrow's lecture starting with this, but the fact that you can construct the state is actually not the same as the fact that you can detect the state. We were discussing a little bit earlier how in Minkowski space you can actually construct all states by just acting with an arbitrary open set. But it's clearly not true that in Minkowski space this little space here has information about what's happening in the whole world. But it's still true that if you act with operators from the algebra of this room, you can generate all states in the Hilbert space. I mean, that's a result in Minkowski space quantum field theory. But it's certainly not true that by sitting in this room, you have information about what's happening everywhere in the world. So maybe at the beginning of tomorrow's lecture, we'll discuss this in some more detail and it might become a little bit more clear.
Because it sounds to me that more...
it's a natural question, but yeah, sorry.
Well, it seems to me more of an algebraic statement than as... I can't really see that physical intuition behind it, I guess. The fact that you can construct the state, I think it makes sense.
The physical interpretation actually is in terms of entanglement. It's the fact that there's, the fact that you can construct the states has to do with the fact that there's a lot of entanglement between this region and the rest of the space-time. So that's what the physical statement is, that there's entanglement between the red and the white region. And in this statement, the statement is there's entanglement between the boundary and the bulk. So the physical state interpretation of the fact that you can construct these states is in terms of entanglement, which again we'll discuss tomorrow. So it's not in terms of information, it's more in terms of entanglement.
Okay, great. Thanks a lot. That helps.
Okay. Okay, great. So I guess we can